This is a talk about Polyglot and how we're taking the ideas of the very oldest approaches to Polyglot and applying some of the newest approaches to Polyglot to make it work well. I work for Oracle Labs, which is the research part of Oracle. We'd come up with new ideas that may become products in the future or may not. So Oracle wants me to let you know that you shouldn't buy Oracle products or stock based on the idea that this will become something that you could actually use in the future. It's just research at the moment. So I want to talk first about why people program in Ruby. At a conference like this, where we're talking about lots of different languages, it may be tempting to think about why can't we just have one language everyone programs in and does everything perfectly. I think it's important to celebrate the fact that we have this diversity in languages and to talk about the fact that people want to program in different languages for different reasons. If people appreciate programming in Ruby, if it fits the way they think, if it fits the sort of problems they have, then it's fantastic. And what we should do as language implementers like myself is help them do that, provide them good tools, good performances to do it, rather than telling them to move to a different language or to even do things in a different way in the same language. We'd like to enable and help people to do things in the way they want to do them. But the problem is what happens when you reach the limits of this approach. A language like Ruby has lots and lots of advantages, but it does have disadvantages as well. And some of the limits that people reach are in terms of the performance they can get out of languages like Ruby and Python. They can't always get the performance they'd like from using the language as it's designed. And we know people are reaching these limits in practice because there are lots of people spending lots of time and effort trying to improve the performance of languages like Ruby. I'm just going to talk about Ruby in this presentation, but a lot of this stuff applies to other languages like Python as well. So in the Ruby ecosystem, we have people in the core implementation of Ruby, MRI, who are working on trying to make it faster. They're trying to add a JIT to MRI. They're trying to add some new techniques such as bytecode specialization, which are quite advanced. For a long time, there's been JRuby, which implements Ruby on the JVM to try and speed up Ruby. There's Rubinius, which is Ruby which used to have a JIT in LLVM. There's other people such as Atver, there's Maglev, which was Ruby on a gemstone virtual machine. There's the OMR project, which someone mentioned, which is IBM trying to add a JIT to Ruby. So there's lots of people trying to add new technology to Ruby to make it fast. But there's a technique that has been used in the past to make Ruby fast and people are still using today. And it's quite a novel idea in a way, but people have been doing it for a long time. And that is Polyglot. What people have been doing is they've been writing extensions to Ruby in C instead of using pure Ruby to help make their programs run faster. So if you have part of your program written in C, the idea is C generally performs better, so your program will perform better. I think the best example of this being done is a couple of pairs of libraries I found. Chunky PNG and Oily PNG is one of them. So Chunky PNG is a library for working with PNG files, the graphics format, reading them, writing them, editing them, making changes to the image, things like that. And that's written in pure Ruby. So that means people who want to work in pure Ruby can do. And people who only know Ruby can understand this code and understand what it does and use Ruby tools on it. But if you want a little bit more performance, if you're reaching that limit of what Ruby can do, then there's another library called Oily PNG, which includes a C extension to make various little parts of Chunky PNG faster and to remove a few of those little bottlenecks that makes a program in Ruby usually pretty slow. But the great thing is that Oily PNG is an overlay on top of Chunky PNG. It just replaces a few key things. It doesn't re-implement everything, and it doesn't change the way the library works at all. It just fits in using monkey patching to replace a few key methods to make it faster. And I think this is a fantastic way to write a C extension, and it's a fantastic way to do Polyglot, and people have been doing it for quite a long time. So Polyglot may seem like a new interesting idea, but really people have been doing it, and sometimes in quite interesting ways for a long time. There's another library, PSD, that comes in a pair, PSD and PSD native, and again this monkey patches. And this is a library for working with Photoshop files. So these are two examples of the limitations in Ruby in that it's image processing, and that's where you reach a sort of limit. So here's a concrete example of what these two pairs of libraries are doing. From PSD RB, the one which deals with Photoshop files, there's this clamp method, which is used in the very inner loop of processing Photoshop files, and it clumps a value between a minimum and a maximum. So it's never less than the minimum, never greater than the maximum. But if it's in between, you get the value which you put in originally. And this has been written originally in Ruby in a very idiomatic Ruby way. What they've done is they've used the core library, they've created an array data structure of the 3 numbers, they've sorted it, and they've taken the middle one. And I think that's quite a neat little way to write this routine in one line in Ruby that people can understand, and it uses the core library. That's good, I think. But it doesn't perform very well. So the PSD native, the C extension, comes in and it replaces this one single method with C. So you still have the same parameters, but this time they're expressed as a C parameters and a C function. So you still have the number, the minimum, and the maximum. And what we have to do now is some extra work, though, because C is lower level. So this function, for example, takes a self parameter as well, which is implicit in the Ruby version, but made explicit here. And to get raw C types out, we have to use some macros to get those values out. So we call fix2int to convert a Ruby fixedNum object to a cint primitive value. And then we do some logic to clamp it between them. And that does exactly the same thing as the Ruby version. So the interface hasn't changed, but it generally performs faster. The way we use this is in the pure Ruby version, we have a Ruby program which runs on top of a Ruby interpreter. So you simply input the program and any input data you have down into the interpreter. When you write the C extension, the model is different. So although the interface is the same to the code and things like that, we deal with the C extension differently to we deal with the Ruby program. And this is where things start to become a bit unequal between the Ruby and the C. So here we input the C program to a C compiler. We get out of that a shared object library or a dynamic library on Mac or DLL on Windows. And then what you do is you plug that into the Ruby interpreter, and you effectively sort of make a new Ruby interpreter that includes your methods. It plugs in at the implementation level. And this is asymmetrical. I would rather this wasn't the case. The Ruby code is being handled differently to the C code is. But this technique does work really, really well. So I created benchmarks from all the routines that these 2 pairs of libraries replaced with C. So I knew they were the important parts of the library people cared about enough to have profiled and found them. And this is the performance of them in iterations per second. In the pure Ruby version, running on the standard Ruby is called MRI, and running with the C extension. And it's around 10 times faster. So the technique works well. The limitation is we just have this asymmetry here. And the other problem is that this has created a long-term problem of technical debt. So I've described to you, you can write these C extensions using these macros, things like that. So you may think that there's a sort of C extension API there, which you program against when you write your C extension. And you use certain calls, things like that, and that communicates with the Ruby interpreter. I also said that there were multiple implementations of Ruby, like JRuby and Rubinius. So you may think that because we've got an API, that's fantastic. We can swap out the implementations beneath them, and you can use your C extensions with the different implementations. And this is really important that we'd be able to do this because as we've replaced code with C extensions, that code has now become a critical part of our ecosystem. Not all C extensions are so well designed as the chunky and the oily examples. Sometimes there is no equivalent Ruby code. There is only C extension code. So it's essential that we're able to run that C extension code on the other implementations of Ruby. But the bad news is that API isn't really a thing in practice. There's no such thing as the C extension API in Ruby. There is a set of header files, and they do try to define what you should use from the header files and what you shouldn't. But in practice, people just use absolutely anything that they can find in the headers. And even critical parts of the ecosystem use stuff from really deep inside the internals. They're not going through that API. Really, it looks a bit more like this in practice. The C extension has many, many tentacles coming out of it, and they reach down into the implementations of Ruby and pull little levers and push things and poke things and read things and write things all over the place. So there's no clean API, there's just a whole lot of tentacles coming out. And the difficulty, the technical debt, is that for another implementation like JRuby, which wants to allow you to run C extensions, it has to provide all those little knobs and buttons and levers and places you can read and write. And there's this huge number of tentacles coming in, and they're trying to think about how do we implement all those? How do we provide all these places that the things hook into? And that's where the challenge is. And it's not just a challenge for the alternative implementations. This isn't the case of the alternative implementations whining that they can't implement stuff because they do things differently. It's not a problem they've created for themselves. It's a problem that Ruby has in general. As Ruby, the language, wants to evolve, as they want to add good new features to the language, they may themselves find that they're limited by these tentacles they've got coming into them. It gives them less freedom to change how things work themselves. As they want to add a JIT, as they want to add new approaches to concurrency, they may find they're limited to doing that by this old API. So I can give you a couple of examples of how extreme this problem is. So we've got some code that deals with strings. So we've got something that does, this is part of the OpenSSL C extension. And what this does is it takes a password in as a Ruby value, and it wants to pass that to the libSSL that's native on your system. So it needs to convert it from a Ruby string to a character pointer. And Ruby provides this macro, rstring pointer, that gives you that. In MRI, this is really easy. All they have to do is provide you the internal character pointer, which is there anyway. But the really tricky thing is, notice, I'm not just reading this password value, I'm actually writing it out as well. So I'm passing the password pointer in, and libSSL, the native code, is writing into this value. So if I want to implement this in JRuby, I need to provide a JRuby string, which is really a Java byte array, as something which can be written to by native code, and that's not normally possible. So what implementations end up doing is they have to copy things from their managed environment to the native environment, so the native code can work with it. And this kind of copying, it immediately sounds like a bad idea. We'll have to copy all our data back and forth all the time. We get the same thing with array pointers. The Ruby C extension API, as it is, provides a function, macro which lets you read the direct pointer to the internals of the contents of a Ruby array. And again, you can read and write this. Here we take actually an internal pointer to the array, and then we read and write that as part of a loop. This works on MRI because MRI arrays are simply arrays of full Ruby objects. But implementations that want to optimize Ruby and make it faster don't want to do that. They want to do more sophisticated things, such as have an array of unboxed pure integer values or unboxed pure double values. If they have to provide a full raw native pointer to a contiguous set of values, then they can't do that optimization. It gets even more complicated. The Ruby C API exposes this structure called rdata, for example, and now it's not just about single pointers. Now we're letting C extensions depend on a particular layout of structs that are used to particularly implement certain features in MRI in a particular way. And here, this is a good example of things being tricky, because if you notice the macro that we use to get the pointer to inside a data structure is actually on the left-hand side of the assignment. So I can't even replace the macro with a function call that copies something for you. It has to be actually a C value that's assignable. It can't be a function call because you can't assign to a function call. So this is even more complicated here. And there are some things that when you write a C extension are actually slower than Ruby code. For example, in Ruby code, when you call foo.toString, we're doing a method call, which means you have to do a method lookup. But in Ruby, normally we cache that lookup. We determine what method to call, and we call it again the next time you make that. But when you do RB fun call to call a method in C, there's no way to store that caching information. So as we add techniques to Ruby to make it more sophisticated, such as inline caching and method inlining and things like that, the C code actually starts to fall behind because we can't do those optimizations. Another problem is that the C code in a C extension becomes a black box. If I've got Ruby code that looks like this and add, and I call it with two particular numbers, then I can look at that and my compiler can work out what that equals. Even though we're going inside a method, we can still work out what that equals. But if I combine C code with Ruby code, then my compiler can't look inside the native code in the same way and work out what it equals. The native code becomes a black box. And if you have too many C extensions in the way, that stops a sophisticated Ruby implementation being able to optimize anything. And it means we grind to a halt really quickly. So we've got a really interesting problem here in that the the current workaround we have to Ruby and similar languages being slow is now actually preventing the problem being fixed properly. As we try to make more sophisticated implementations of Ruby, we're stuck to what options we have for optimizing, and we're stuck for the performance from C extensions. So we can't solve the original problem because the original workaround is in our way, which is a classic kind of technical debt, isn't it? You'd like to do things properly, but you can't because of the way things were done in the past. So how are people trying to solve this? There's a number of approaches people are trying. The first one is denial. People are denying the problem. Some people say everyone should use the FFI or fiddle. In the LLVM talk, we talked about the FFI and how it was a nice, proper way to make calls to native code. That's fantastic. Fiddle is a sort of equivalent thing to the FFI. But there's 2.1 billion lines of code in Ruby gems, the Ruby library repository, and 500 million of it is C extensions. So if people aren't using the FFI, we might like them to, but they're not much we can do about it. I can't personally go around and berate them all and get them all to use FFI instead of C extensions. And this is part of what I mean about we should accommodate how people want to program languages rather than telling them how they should do it instead, and try and make it fast for how they're doing it. Second option is bargaining. So we could attempt to implement the C extension API as best as possible alongside doing our optimizations. Generally involves a lot of copying. JRuby used this approach in the past. It's had an extremely competent person spend a lot of time trying to implement the C API on top of JRuby. It worked. Rubinius does something similar still to this day. But when I tried it, JRuby only ran about 60% of the C extensions I tried. Rubinius was better about 90%. But the worst thing is they didn't stop working with an error. They just sort of ground or halt as the level of copying they had to do sort of built up and built up and built up. So that's a really bad failure state to just sort of stop working over time rather than just giving an error message. We can try and improve the C extension API. So the JavaScript V8 API that Node.js uses and the Java JNI interface are much better designed. But again, that's just wishful thinking. The Ruby API isn't designed like that, so nothing we can do about it now. And there's steady progress towards adapting it over time, but even things like the OpenSSL gem don't use it. So there's not much more we can do. So depression. JRuby unfortunately had to give up on their C extension work. They didn't have the resources to maintain it. Limited compatibility, limited performance, and performance was the whole point, remember? In the end, it was just removed entirely. Maybe they'll try it again in the future using a similar approach to what we do. And acceptance. So JRuby now encourages Java extensions instead of C extensions. And we could try and optimize Ruby while keeping the internals the same, maybe. That's what IBM's OMR project to add a JIT to MRI does. But the techniques are limited, and therefore the performance they can hope to gain is also more limited, I think. And this is the problem in terms of performance. We said that we get around 10x improvement when we use C extensions on the standard implementation of Ruby. When we use JRuby's attempt to implement the API, performance is much more limited. It is a bit faster than using pure Ruby, but it's not what we were originally going for. And JRuby is even worse than Rubinius, which is a shame. So I'm going to introduce two components here, which are about addressing this problem. The first is Truffle Ruby. Truffle Ruby is a new implementation of Ruby on top of the JVM using a couple of new pieces of technology. The big idea and the big motivation here is that the JVM is generally a black box for language implementers. When you want to implement a language on the JVM, the sort of best thing you can do at the moment is you can pour bytecode into the top of the JVM. You can emit bytecode at runtime and pour it in. This is what Jython do and JRuby do. And inside the JVM somewhere is a JIT compiler, a really excellent JIT compiler. But the only interface you have to it is pouring bytecode at the top. You hope that your bytecode will reach the JIT compiler eventually, but it's a pretty torturous route to get there. You have to have a really good understanding of why it might not get there and what to do about it. And there's only a few people in the world who know how to do that sort of thing really well. People like Charles Nutter on the JRuby project know how to do it, but even for him, it's a lot of work and frustrating, obviously, often, I believe. Our big idea in the Growl and Truffle projects, which we'll be hearing more about tomorrow from Gilles, is to take the JIT outside the JVM. Let's not have it as a black box. Instead of having it written in C++, where it's hard to understand, hard to work with, let's rewrite the JIT compiler into Java instead. And that's not just an exercise of doing things in Java for the sake of it. If we write it as Java, then it can be a Java library instead of just being a C++ component inside the JVM. So that means instead of just pouring things in, we can communicate with it on a much finer level. We can give it things, it can tell us things back, etc. We can give much finer control. Doing that's complicated. Working with a compiler that's as sophisticated as a JVM JIT compiler is complicated. So we've built a framework on top called Truffle. Truffle helps you implement a language on the JVM. I won't explain how it works in this talk particularly today, but it's a framework that helps you make a very simple interpreter for your language and then uses growl to make it very high performance. We can achieve performance for this similar to V8 for JavaScript and beating all other implementations for Ruby. So we have the JVM, which contains growl as a compiler. Then we have the Truffle Framework, and what we've built on top of that is this new implementation of Ruby, Truffle Ruby. And I should say Truffle Ruby uses code and ideas from MRI, JRuby, and Rubinius. So I talk about it as a sort of apex implementation of Ruby. It's taking the best ideas and adding new technology and building what we think is the best implementation of Ruby we can. Now the second component here is something called SooLong. I said that the model for C extension was asymmetrical compared to the Ruby one. So we have our Ruby program going into the Ruby interpreter, but for C, we compile it, create a native module, plug it into the interpreter to create a sort of second interpreter. What we'd like to do instead is let's have a Ruby interpreter, which takes Ruby code, and let's have a C interpreter, which takes C code. Let's put them inside the same system, instead of the same virtual machine, and then they can both work as equals. Now, it's actually a little bit more complicated than that in reality. We don't want to support the whole of C because of there's complexities there. So what we do instead is we have your C code, which you can compile down to LLVM bit code, and then we write an LLVM bit code interpreter. LLVM is a framework for writing compilers, generally native code compilers, ahead of time compilers, things like C, C++, Objective-C, but it can be used for a range of things. And one of the things LLVM has is this common way of representing a program that's low level and simple. And that's called LLVM bitcode. So we wrote an interpreter for LLVM bitcode, and you can compile your C code to LLVM and then run that on our interpreter. So that LLVM interpreter, that is SooLong. That is the interpreter we use for LLVM for C. Now, it may sound really complicated. I'm talking about interpreting C. That doesn't sound like something that is possible or people normally do, or at least it sounds like something that would be very different to interpreting for Ruby. No, I want to dispel that myth. So this is our clamp function from earlier in C. What Clang does, the LLVM interpreter for C, is it takes that C code and it converts it to this LLVM IR. Yep, that looks complicated, so I'm going to zoom in a little bit and show you how simple it really is. I'm just going to zoom in on this bit here. So what we have here is some code which looks complicated, but I promise you really it's simple. So what we do here is we can compare as integers the values 1 and 3, which are just temporary local variables. They have numbers rather than names. And we branch based on the comparison. We go to either 5 or 6. And then at 5, we branch again to 12. If we don't branch to 12, then we assign 7 to the comparison of 1 and 2. And we branch again based on that. Now 1 is the value, 3 is the maximum, and 2 is the minimum. So what we're effectively doing here is we're saying T4 is T1 greater than T3. If that was the case, go to L5, else go to L6, and then L6 is T7 is T1 less than T2. If something, go to something else. So if you know basic, or if we imagine Ruby has go to, and Ruby does have go to, by the way, there's a switch you can use to turn it on, but it's non-standard, then you can see how that code that looks really complicated and technical on the left, actually it's just like basic code or a really simple version of Ruby. So we could interpret that. We could write quite a simple interpreter really to execute that kind of code. Although the text representation looks complicated, the semantics is actually not exceptionally complicated. So what this allows us to build is a true idea of Polyglot. It allows us to build Ruby and C as equal languages working together. So as I said, the original idea was that we had Truffle, which talked to Growl on your behalf, working with the JVM. And what we have here is we have both Truffle Ruby, the Ruby implementation, and SooLong, the LLVM interpreter implementation, both on top of Truffle. And that means that Truffle can work with them both together at the same time. It can understand both of them, it can manipulate both of them. And when it talks to Graal, it talks to Graal on behalf of both of them at the same time. So if we have a Ruby program that contains lots of Ruby methods that call each other, and we have a C extension, C program that has lots of methods that call each other, what we can do is we can apply optimizations across them at the same time. So this is now a polyglot language interpreter, a polyglot virtual machine that's supporting both these languages at the same time. And we can do really sophisticated things, such as we can combine Ruby code and C code together in the same compilation unit, and we can inline from C into Ruby, back into C, back into Ruby, etc. if we find that makes sense, and that's something we'd do when we were compiling code if we saw it based on profiles and things like that. So we now have a system where we've removed that black box between the two languages, and we've removed the inequality between the two languages and made them two equal languages working in the same way. So let's talk about some interesting problems and their solutions. One interesting thing we can do is we can define the C extension API in Ruby now. So instead of having to write a lot of C code that sort of calls back into our Ruby implementation, we can simply do the whole thing in C or Ruby at the same time. So Ruby has this function in its C API fixed to int, and we've implemented that by a little stub of C code which says invoke in Truffle in the C extension module that method with that name, and then we implement in Ruby a module of C extension functions, and we implement the logic there of fixed to int, which involves checking if the value is a nil. If it isn't, convert it to int, check the range, and then return the value. So instead of having to write more C code apart from that tiny little stub, we're now enabling people to do that in Ruby. So the C extension logic, which before was in C and was hard for people who didn't know C to understand, is now done actually in Ruby. And the code which optimizes this can optimize through this C code, through this call, even though it has a string as a name, into the Ruby code, all as one. A second interesting problem we have is that I said that the way that the Ruby API allowed you to access string pointers directly restricted what we could do with strings and similar to arrays. One of the optimizations we have in Truffle Ruby, ignoring the C extension API for a minute, is we'd like to represent strings as something more sophisticated than simply a contiguous array of characters. The C API allows you to access a particular character directly, so it's a sort of assuming that there's a contiguous array of characters there. We use this representation of strings in Truffle Ruby called ropes, where we represent strings as trees, basically. When you concatenate two strings, we don't copy them into a single piece of memory. We simply remember that this string's being concatenated. So when you're building up something like a template, you simply have a tree of concatenate nodes rather than allocating more and more memory. Kevin Menard talked about this at Ruby Kaige 2016. But how do we implement this using the C extension API? Well, what we've got is you want a reference to this contiguous memory, but actually you only have a node that links these two strings together. What we do is the LLVM IR, which reads from a pointer, so get element pointer, so it passes in the pointer is the start of the string and reads a particular character. What we've done is we've said that if you use get element pointer on a Ruby string, actually redirect back into the Ruby code and use the normal string indexing routine, which then knows about how to navigate these trees. So what we've done here is we've sort of virtualized the C. You think you've got a C pointer that you're indexing like you would any other pointer in C, but actually when you do that, the operation goes off and executes whatever logic we like, which in this case is indexing the string using the normal indexing operator in Ruby. Let's talk about some results of this approach. So we talked about these numbers before, where we have MRI with pure Ruby. We add a C extension that makes about 10 times faster. The two previous approaches haven't worked very well and don't deliver the same kind of performance. When you run Truffle Ruby with a C extension, we're actually faster than the native code. And then when we also tried Truffle Ruby with disabling inlining between languages. So I'll talk about these results in turn. Native C extensions do give an order of magnitude performance boost, so they work at the moment. The previous two attempts to mix Nanish and native haven't worked very well. But when you use our approach, you're 3 times faster than native. How are we faster than native code, even with a great JIT compiler? Well, the reason is that we're able to inline from C code to Ruby code back into C code. So these benchmarks spend a lot of time going between the two languages to run the C extensions. And we're able to inline that into a single unit because we use this uniform way of representing the programs. And we verified that that was what the important bit was by we disabled cross-language inlining. We found the performance was a bit more limited, but actually even with that disabled, we're still 10 times, we're still about faster than the MRI with C extensions. Limitations. So I won't pretend this is an absolutely perfect solution to everything. One of the limitations is you do need the source code of the C extension because we work with the source code rather than native compiled code. I'm not really sure this is a problem for anyone in reality. I'm not aware of any closed source C extensions. Maybe there are, but we wouldn't work for those. C extensions in turn using closed source libraries like database drivers, however, is fine. As long as all the bits which use the Ruby C API are done using our system with SooLong, then it's fine. You can call out to actual native code for things like database drivers. Another limitation is that you can't store pointers to Ruby objects in native code. So if you're using a compiled library like libssl.so, you can't give the compiled library a reference to your Ruby object because your Ruby object may not really exist anywhere in memory. And the GC won't want to move that object while it's in native. So a limitation is you sometimes have to modify your C extension code to add native handles. So if you pass an object to manage, then you have to call to native handle, and when you get it back, you have to call from native handle. In this example, we're setting some extra data on SSL extensions, and we have to use the handle instead. So that is unfortunately one limitation. If you were to run your native library as well as the C extension part in SooLong, you wouldn't have that limitation always. But sometimes you want to run native code. You may not have the C code behind it, something like that. So to summarize, what we've done here is we've created a system that allows us to place 2 languages in a polyglot situation on the same level, using the same system and interacting and optimizing in the same way. And people have been using this form of polyglot for a long time, C extensions. And what we're doing here is we're using some of the newest ideas in virtual machine implementation to support this old use case. And in doing this, we're enabling people who have existing Ruby programs that they want to keep running, or enable them to get the performance increase that they want while still using that legacy solution. And I think that's fantastic because it enables people to keep programming the way they want to program or the way they have to program because of externalities, but still get that performance increase. And I think that's a really important thing for language researchers to be thinking about. Where to find more information about this? All the things I'm talking about today are available as open source. So if you search for GitHub Truffle Ruby, you'll find the source code of our Ruby implementation, Truffle Ruby. You can do the same thing for SooLong. You'll find our implementation of SooLong. And I encourage you to go and look around in these repositories. These are language interpreters written in Java in a fairly high-level way. You won't find any assembly in these projects. They're very simple to understand projects. If you've done an undergraduate's course in compilers, you've probably heard about AST interpreters. It's the simplest form of a way to implement a language, basically. And these are both AST interpreters. And you can get everything packaged together as one module you can use. If you search for Oracle Growl, you'll find where you can download that. It's equivalent to using like a JVM. I should say there's a very large group of people behind this. This is just a few of them. This is the entire list of people who have worked or are working on this project. So it's a large number of people. I'm just the one here standing here today talking about it. Thank you.